Okay, when doing implicit differentiation, which is basically a way of saying I'm going to do derivative, and it doesn't matter whether it's set as y equals or x equals or whatever, our goal is still the same. Our goal is still to find the slope. We still need to find the derivative, which, of course, we want the slope. That's when we find the derivative. But what happens when you have an equation, such as you see in this first example, that isn't set equal to y? Obviously, our first method could be solve for y and solve for dy dx. The second thing is we could graph it, and we could actually do the reciprocal of its slope. We could find 2 points, and we could actually do find the slope, rise over run, and then do the reciprocal of its slope. The other option is to do implicit differentiation, and I want to show you what this means. What we're going to do is we're going to find the derivative of this function. And so what that looks like is we are going to find its derivative in each of its parts. Now, what I'm going to do, and hopefully you recognize this to be true, you know that this is the same thing, dx, as if I wrote f of x instead of that y. And I hope that that will maybe enlighten you a little bit as to why I do certain things as we move forward in this. So what I'm going to do now is I'm going to find the derivative. And this is the derivative of y in respect to x. Everything is in terms of x. All right, so when I do the derivative, I am going to get 2x. That's obvious, right? The derivative of x squared is 2x, no problem. Where things get a little weird is when it's not written in the form of just an equation with just x. If it's y squared, or if it's a z, or if it's a q, or if it's a p. What do we do when it's a different function or a different letter here? Well, to do the derivative of this would mean that we're going to go 2 times f of x, whatever that function is, times the derivative of the inside, or the derivative of that function. So we would have to take care of the power, and then we would drop that in front, so that's 2 times, and then we do the derivative of f prime of x. That's the chain rule in its finest. Does that make sense to all of you? Now, what that would look like involving the y, let me just show you. If instead we're talking about x squared plus y squared equals 25, what that would look like instead when we do the derivative would be you'd still have the 2x, but what we would do is we'd say, all right, that derivative of that is 2y, but remember that's not an x, and we're talking about in respect to x. So we would have to do dy dx, whatever the derivative of, that's what that notation is saying, the derivative of y in respect to x, whatever that function is, f of x, same thing as you see here, that's what that dy dx would represent, equals 0. Looks very close to the same thing. Now come back to this left-hand side, this one that's on the gray. Once you see that, if we're doing this at the 0.34, then it's pretty simple what we're doing. We're just going to plug in place of x, you're going to plug in 3. So 2 times 3 plus, right, 2 times f of 3, because that's what x is, times, and then the derivative of f prime of 3, right? Or f prime, sorry, not the derivative of it, but f prime of 3 equals 0. Okay? Now remember, what we're trying to find is what is the slope, or f prime of 3. This is what we are solving for. So what we're basically going to do is say, okay, this is 6 plus 2. F of 3, we know from the point, is 4 times f prime of 3 equals 0. So we have 6 plus 8 times f prime of 3. All right, now we're going to move this 6 over to the other side, and we're going to solve for f prime of 3. So I have f prime of 3, and I'm going to leave the 8 there, equals negative 6, and I'm going to divide by the 8. And so in other words, f prime of 3 is equal to negative 6 over 8, or negative 3/4. And that is the answer I'm looking for. In looking at the right-hand side, the only difference would be you're going to solve for dy dx. So just pay attention to this. This is watch how this plays out. You have 2 times 3, because that's what x is, plus the y, which is 4, dy dx equals 0. So you have 6 plus 8 dy dx. And you can see the parallel now with the previous one. We're solving for dy dx. We just don't know what that derivative is. That's what this is asking for. The slope at, in other words, f prime of 3. That's what it was asking for to begin with. Now, the only difference is to answer B for 3, -4. Again, just like we've talked about in previous ones, you have to kind of have an understanding for the graph and know where 3, -4 is. One is going to be positive, one's going to be negative. But the slope will be, in essence, the same, 3/4. It's just one's going to be positive and one will be negative. Now let's look at number 9 from your homework assignment. In number 9, you did this question already where you solve for y. And I just want to show you how much the same this actually turns out to be. When you look at number 9, you solve for y and you actually did it out and you got the -3/√7, right? So now let's try and look at this question a little bit differently. So now we're going to do it using implicit differentiation. When I do implicit differentiation, again, I'm going to just leave it in the form with the y. So when I do the derivative, it's going to be 6x. And since that was in terms of x, we can leave it just like that, plus. Then this will be 2y, but this is not an x, so we're going to throw on there the dy dx, or rather the derivative of y in respect to x, equals the derivative, which is 0. Okay, now we're going to solve for dy dx. Some people, especially when you're not given the point, some people prefer instead to solve at this point for dy dx. So you have 2y dy dx equals -6x. Now we'll divide by 2y. So dy dx equals -6x over 2y. And so now when it asks the question, all I have to do is plug in the x, plug in the y, and I've got the answer. And there is your slope at the point -1, 3. Isn't that interesting? So you have -6 times -1 over 2 times 3. And so you have 6 over 6. Oh, sorry. Yeah, which is 1. There you go. All right. Let's try a more advanced one now. Some of these are going to get very cumbersome where you cannot get y alone without a lot of algebra here. So this provides to be a much easier method in doing so. All this is asking me to do is define dy dx. So as I do the derivative of this, you have to keep that in mind. You're just solving for dy dx. So watch how this plays out. We're going to do the derivative. And remember, we have a product rule here. So I'm going to do the first times the derivative of the second. When I do the derivative of y cubed, that of course is 3y squared dy dx plus the second y cubed times the derivative of the first, which would be 3x squared, minus the derivative of this next part would be 3, but it's in y, so we're going to do dy dx equals, now we have, again, the product rule, the first times the derivative of the second. The derivative of y is just 1, but we'd have dy dx plus the second times the derivative of the first, plus the derivative of 5x, which is 5. Now what you want to do is to neaten this thing up is you want to basically get your dy dx's all together. You want to get all of them either to just the left or just to the right. You want to kind of order things a little bit nicer. So here's how I'm going to do this. I typically will bring everything to the left-hand side. I will bring all the dy dx's to the left, and everything that doesn't have a dy dx will go to the right. And as I do so, I'm actually going to take it a step further in neatening things up and put the dy dx just out in front so I don't have to rewrite it a bunch of different times. So what I'm saying here is this first term here has a dy dx. So that's going to be 3x cubed y squared. This next term, I know I'm going to be moving to the right. Then I have minus 3, because that has a dy dx, right? Then I look at this next term, it has a dy dx, so I've got to move it to the left-hand side, so it's going to be a minus x squared, and the dy dx would play out in front. Everything else that you see there is going to be held on the right-hand side. So now I'm going to put my equal sign. Again, I recognize that this term here, y cubed 3x squared, rather 3x squared y cubed is going to appear on the right-hand side, and it would be a negative because that's how we brought it to the other side. Plus, we have 2xy plus 5. Now, if I want to solve for dy dx, what have I got to do with all of this? Good, divide. So I'm going to divide both sides by that amount. And so this whole piece is going to appear right below. And this would be my final answer. This is what equals dy dx. Fancy, huh? Let me just do one more with you. All right, the derivative. First times the derivative of the second. Feel free to do this, by the way, on your own, and then come back and check to see if you get the correct answer. But I'm just going to walk you through it. Plus the second times the derivative of the first. And the derivative of x is just 1. And we don't need to put dy dx because it already is with respect to x, so we don't have to adjust anything. Plus the first of this next one times the derivative of the second, which is 1, but dy dx, plus the second times the derivative of the first, equals, derivative on the right-hand side would be just 3, but then we'd have dy dx. Again, like I said before, we want to get dy dx alone. And so what I'm going to do is group everything that has a dy dx together on one side, and everything that does not have a dy dx will go on the right-hand side. And so what I would have is a negative y squared minus 2xy. And so what I'll end up doing is dividing by this here. And so it would become 2xy plus x squared minus 3. And certainly we would look at the choices for multiple choice to see if any of those match up. If any of them actually, you know, maybe a different order, like x squared plus 2xy minus 3 in the bottom, or anything like that. So hopefully that gives you enough examples for you to see implicit differentiation, and that's what we will be working on in the days ahead.